Okay, very good morning. So nearly 28 members. Okay, let us start our today's session. I'm going to share my screen. In the previous classes, we have seen from the beginning of this control systems. So we have considered a physical system, from that physical system to a physical model, and physical model to a mathematical model. Okay. So once we get the mathematical model means a transfer function model. So to get a transfer function, we have learned how to represent a mathematical equation using laws. Okay. And from that mathematical model, we can also represent the same in block diagram fashion or signal flow graph method. After getting, so from reducing using block diagram reduction algebra, we have obtained transfer function model. Next, similarly, by applying Masson-Square formula, we have obtained transfer function model. Once we get the transfer function model, next, our aim is the response of the system. So the response is mainly depends upon the type of the system and also the input. So once you give the input, so you will get the final response. To analyze that particular response, okay, so we have specified some specifications. They are called time domain specifications. Time domain specifications for a second order system we have seen, and for a time domain specifications, we have derived the equations for second order system when the input is unit step. Okay, next, number 219 20B8 5A0219. Please unmute your mic. (219). Switch off your mic. Okay. So once we get the response, we can represent using time domain specifications. In that, we have derived formulas for second order system, because most of the system are of underdamped systems and the response is damped oscillatory response for any practical system. So that's why we have considered the damped oscillatory response, and that is specified using rise time, peak overshoot, settling time, and also the steady state error. These are nothing but the time domain specifications. So we have derived formulas for second order system when the input is unit step input. Okay. So after that, the steady state error, it represents the quality of the response system. Okay. So steady state error gives the quality of the response, whether it reaches the final value or not. Okay. So that is we have learned. Now we are going to, it is very important. Steady state error is very important in control systems, whether it is follows the input or whether it is reaching to the desired value or not. Okay. So once we get the steady state error, that can be represented using either static error constants and also the generalized error constants. In the previous sessions, we have derived formulas for static error constants and also generalized error constants. Okay. So now once we know this static error constants or generalized error constants, we can find out steady state error. Okay. And once we know the transient response specifications, that means the peak overshoot values, rise time values. So everything, if we know the values, we can speak about the stability of the system. Okay. So now coming to controllers. Next topic is response using the proportional integral and proportional derivative controllers. And also PID controller is also there, proportional integral derivative control. So what is its function? So still now when the some input is given to a system, so you will get response. We have analyzed the response. Now we are going to adjust the response. Okay, depends upon the requirements. So here, just see here. For the satisfactory performance of the control system, it is convenient to adjust. Adjustment is made between the maximum overshoot, because the maximum overshoot must be less for an ideal system, and steady state error must be 0 for a ideal system. So this is the response what we have seen in the previous classes. This is the response, a damped oscillatory response before it reaches to unit value. So an oscillation takes place and finally it reaches to settling value. Okay, so for an ideal system, so this is the response within no time. So rise time must be 0. Okay, overshoot, this is maximum overshoot, that must be 0. Okay, and also the settling time must be 0. So within no time, this is the output C of t response. Okay, so if input is equal to step input, so output must be the same. So it is also a step just like this. Within no time, it has to reach maximum value, final value, and it must be settled at that value. So it is not possible ideal case, but most of the cases, critically damped case, if we observe without any oscillations, that means the maximum overshoot is less, rise time is also a little bit less. So we have to compromise, we have to adjust the maximum overshoot and steady state error. Okay, so just to adjust this to get the required values, to get the required response. Okay, so maximum overshoot can be reduced to some extent by modifying the actuating signal without sacrificing the steady state accuracy. Just a minute, wait. Okay, now so just by adjusting, are you able to hear? So just by adjusting the actuating signal, we can get, so we have to reach the steady state value. Okay, so here our aim is to adjust, minimize maximum overshoot. So within minimum time it has to reach the final value. Okay, so the steady state error must be 0. So everything should be minimized at a time. So that is our aim. This can be possible by adjusting the actuating signal. Actuating signal means, so which is given to the plant. So here this part is called as controller part. Okay, just we have added. So previously only R of S input, C of S output, forward path transfer function, feedback transfer function. Now by adding this part into the system, so that we can adjust the output response, okay, to get the desired value. So here the actuating signal is directly proportional to error signal. So this is called as proportional controller. Here this is actuating signal. Actuating signal means actual input given to the system. Okay. Here the error signal. Error signal means the output. The difference between the output and reference input. So difference between these two, you will get error signal. Okay. So the error signal here in proportional controller, actuating signal is proportional to the error signal. Hence the name proportional controller. Okay. So this is called as proportional controller. Now the transfer function for this proportional controller is, this is the transfer function. Only a constant value. Proportional controller means, so here the input value, so this is error signal, E of S, actuating signal, EA of S. By adjusting, if I want to adjust this actuating signal, just by changing this KP value, which is called as proportional gain. Okay, we can increase or decrease this KP value so that the output response can be adjusted. So here is the explanation. Just see, for a quick response, it is necessary that control system should be underdamped. So we have already seen, for an undamped system, when zeta is equal to 0, system is oscillatory response. When system is underdamped system, so that means when it is less than 0, less than 1. Okay, so it is, so here it is oscillatory response. So when zeta is less than 1, so damped oscillatory oscillations, they will get reduced. Next, when it is critically damped, so the system becomes, when zeta is equal to unit value, the response is something like this. So not like this, actually, strictly speaking, that is something like this. Okay, when zeta value is more than 1, greater than 1, here it takes more time to reach this final value, sluggish, slow system. Okay, so as zeta value increases, the system becomes slow. Okay, when zeta is equal to 0, it is damped oscillatory, very fast it reaches. Okay, when zeta is less than 1, it takes less time, a little bit more time to reach this final value. This is rise time. Okay, so when zeta is equal to unit value, it takes more time to reach final value. Okay, so here is the, for a quick response means, so it has to reach final value within less time. Settling time must be less. Okay, immediately it has to settle. So it is necessary that the control system should be underdamped. Only for underdamped system, that it is damped oscillatory system, so it is, so a little bit faster and finally reaches to settling value. An underdamped control system has an exponentially decayed oscillations in the output during the transient period. So here your second order system, so this is the response damped oscillatory. So damped oscillatory response. uh, oscillations decay in the output during the transient period. So during transient period, it reaches to 0. Okay. So next, the sluggish and slow moving overdamped system, overdamped response of a control system can be made faster by increasing the forward path gain. Okay. So just if I want to, if we increase k value, okay, the slow moving, so if we increase k value, what happens? The overall transfer function, gain of the transfer function increases. Okay, so once the gain of the transfer function increases, zeta value decreases. Okay, if we calculate zeta value, so its value is going to reduce. The sluggish or slow moving overdamped system, so this is our overdamped system. When zeta is equal to 1, this is zeta is less than 1. Okay, so this is sluggish system. This system is called as sluggish and slow moving system. Even though there is no oscillations, it is reaching to final value, but it is termed as sluggish or slow moving system. The overdamped response of a control system can be made faster. So if I want to make this system a faster response, here this is faster response when compared to this one. Okay, so just I'll draw again the same figure. So this is our second order system response, where sluggish system is, it takes more time to reach final value. Okay, so as zeta value is less than 1, here zeta value is equal to 1. So this sluggish system can be made faster just by increasing the forward path gain of the system. As increasing in the forward path gain of the system, the results in reduction of steady state error, but the peak overshoot gets increased. Here, if we increase the forward path gain, zeta value decreases. When zeta value decreases, overshoots occurs. Okay, even though it is some overshoots occurs. Okay, it goes to steady state value a little bit more faster than this one. Okay, so if we want to get a faster response, if we want to make a sluggish system into a faster response system, so we can add a proportional controller. That means KP is added in series with, in cascade with forward path gain. Okay, are you able to clear? Okay, is it clear? Okay, this is about. So if we want to increase this sentence, we have to remember this. Okay. As increasing in forward path gain of the system resultant in the reduction of steady state error, but overshoots get increased. So we can make a slow system into a faster system if we add a proportional controller. Okay, next. Coming to derivative control. So if we add a derivative term to this same system, second order system. Previously, we have added only one term, that is proportional. Now proportional derivative controller. Okay, here the derivative controller means the actuating control signal consists of proportional error signal and derivative error signal. So both error signals. So here, okay, just please note down this figure. So this is about the derivative control. Here, the actuating signal here this is actuating signal is directly proportional to error. It is derivative of error signal. So derivative means this is nothing but the proportional term. This is derivative term. So here the actuating signal is error signal plus derivative of error signal. So derivative of error signal means t by dt. So this is some constant value td. So if we take Laplace transforms, so d by dt of e of t is equal to s into e of s. So here this is proportional and this is derivative. Okay, so this is also called as proportional derivative controller. So if we keep derivative part is proportional part is unit value, this is simply derivative controller. Otherwise proportional and derivative, if we keep some ka here, kp, so that becomes proportional and derivative control. Okay, so based on this equation we have drawn a block diagram for derivative control. So this is the derivative term. Okay, okay, now the overall transfer function of the derivative system. What is the effect of this derivative control that we have to observe? So previously second order system, without this derivative controller, we have second order system. The response is damped oscillatory response. We have already find out that steady state error value, everything. So now if we include this derivative controller to the system, now the overall transfer function is going to be this value. Okay, so overall transfer function is this omega n square into 1 plus std by s square plus 2 zeta omega ns plus omega n square td into s plus omega. So this is the overall transfer function. Now the characteristic equation means what? So it is the denominator polynomial of closed loop transfer function. This is closed loop transfer function. So denominator polynomial of a closed loop transfer function is called as characteristic equation. So now characteristic equation for the system is this one. So the second term, for if we compare with the standard second order system, standard second order system means the characteristic of a characteristic equation of standard second order system is s square plus 2 zeta omega ns plus omega n square. This is standard form of standard characteristic equation of a second order system. Okay, s square plus 2 zeta omega ns plus omega n square. Here if we write in that same fashion, if we compare, so if zeta dash is the effective damping ratio of second order system with the derivative control, the characteristic equation should be s square plus 2 zeta. So this is zeta dash is damping ratio after adding derivative control. Okay, so if we compare that with standard form, so zeta dash value is equal to 2 zeta omega n by, just a minute. So now if we observe this zeta value, so previous zeta without derivative control, zeta value is zeta, only zeta. Now that value is zeta dash. So if we observe this equation, zeta value increases. If we add derivative control to the system, so zeta value is increased by, so omega n into td by 2, where td is constant value, derivative constant, this is td. So here shows the equation, damping ratio is increased. Okay, damping ratio is increased using derivative control, but the maximum overshoots is decreased. Same thing we have already observed in this response. So this is second order system with zeta value is equal to 1 and zeta value less than 1. So here zeta value increased means a faster system is become into sluggish system. One thing what we have observed, and these oscillations, that is oscillations will get reduced. So maximum overshoot is reduced. There is no overshoot when zeta is equal to 1. In this case, there is overshoot. Okay, so maximum overshoots can be reduced and zeta value gets increased. That's what we have observed in this derivative control. Okay, depends upon the application, depends upon the required output. We have to add, whether we have to add proportional controller or whether we have to add derivative control or whether we have to add integral control or combination of these things. Okay, these controllers depends upon the requirement, depends upon the response. We have to add these controllers. Adjusting the actuating signal, what we are doing is adjusting actuating signal, naming it as proportional, derivative and proportional integral controllers. So here is the overall transfer function. If we find out the error function for the same system with derivative control, so this is E of s by R of s, whose value is going to be s into s plus 2 zeta omega n by s square plus 2 zeta omega n plus omega n square td into s plus omega n square. So this is error signal. Okay, just note down this one. Okay, so this is error signal R of s for an input for E of s for the given input R of s is equal to this one. Okay, now if we can find out the steady state error, it is going to be 2 zeta by omega x. In the previous case, if we observe while calculating the steady state errors, okay, in the beginning, so steady state error value is the same value. So with and without derivative control, if we observe, the error value is not changed. These are the conclusions. Comparing the steady state error of a second order system with and without derivative control, both the values are same. So even if we derive, if we calculate the steady state error without adding derivative control, you will get the same value. So after adding derivative control, you will get the same value. That means it is not going, derivative controller is not going to affect the steady state error. So whereas the rise time reduces, so it becomes theta rise time is reduced. That means damping ratio increases. Okay. So these are the conclusions. Next, coming to integral controllers. Same thing, same procedure we have to follow. So actuating signal, this is EA. This is proportional plus integral of integral of error signal. So that becomes actuating signal. So integration of actuating signal, integration of error signal plus this is one more error signal. This term is proportional term. This is proportional term. Here this term is called as integral term. So if we add k something kp, otherwise simply if kp is equal to unit value, we can take it as integral controller simply. So for this, here the actuating signal becomes ei into 1 plus ki by s, taking Laplace transforms. Based on this equation, we can draw the block diagram. So here this term is called as error integral controller. This entire thing is proportional integral controller. So this is actuating signal. Again, what we are doing is applying the same thing to second order system, standard second order system. This is okay. Just draw the figure. Standard second order system. So this is integral control. Okay, now the closed loop transfer function. So if we find out the closed loop transfer function means this is eliminating this forward path and cascading these two, and unit feedback system, eliminating feedback just by applying g by 1 plus gh. Finally, you will get this equation. C of s by r of s is closed loop transfer function. Block diagram reduction. Okay. So closed loop transfer function is equal to s plus ki into omega n square by. So here the order of the system, the denominator polynomial, if we observe previously, that is second order system. Now the order of the second order becomes third order system. If we add one more integral term, that becomes fourth order system. If we add one more integral controller, that becomes a fifth order system. So that means the order of the system increases if we add integral controller to the system. That is one conclusion. So higher order systems are unstable when compared to lower order systems. So instability increases. Just note down this one. Okay. Now, again, if we find out error, P of s by R of s, error signal this is. So this is open loop transfer function with integral controller. So here error signal with integral controller, if we calculate for a unit ramp input, limit s tends to 0, s into ramp input means 1 by s square t. Okay, its Laplace transform is 1 by s square. That is going to be 0. Steady state error is 0. Please note down. Okay, next. So for a parabolic input, if we change the input, so again, here 2 zeta by ki into omega n. Here the ki, it is nothing but integral constant. Okay, integral controller constant ki. Okay, so if we increase this value, automatically the steady state error value will get reduced. So we can conclude that one. So comparing the steady state error of the second order system with the integral controller, the steady state error is reduced by integral control action. Here the steady state error can be reduced. The final steady state error can be reduced, but the oscillations, because of this order of the system is increased by 1, the overshoots may be more when compared to second order system. Okay, even though the overshoots are more, the steady state error will get reduced. Steady state error means final value. Okay, so that is the final conclusion in case of integral control or integral action. So if we add integral controller to the system order of the system increases, but the steady state error will get reduced. Previously, in case of derivative control, so here the steady state error is not going to change any value, but the rise time reduces. Okay, so for proportional controller, we can make a faster response. For a slow system, into a faster response. That is about controllers and response of the controllers. Okay, you just go through the textbook, any textbook. If you have any doubts, you can raise the doubts. Otherwise, we'll end this session. So I have given you first assignment. I have posted in Google Class. So kindly go through that assignment. Okay, within 1 week, you have to submit the scanned copy with registered number. Okay, otherwise scanned copy to my register number. So please take my email ID. Otherwise, you can directly connect the same using Google Class, mail chain.